The global aviation industry is undergoing a transformation few could have imagined just a decade ago. At the center of this shift stands the C919, China's first domestically built commercial jetliner, crafted to compete directly with Boeing and Airbus on the global stage. Since entering commercial service in 2022, this aircraft has drawn the attention of airlines, governments, and analysts worldwide. The numbers tell a striking story: over 1,400 orders in just a few short years. For a newcomer challenging two aviation giants that have dominated the skies for generations, this is nothing short of extraordinary. But the C919 represents far more than impressive sales figures. It symbolizes China's determination to enter one of the world's most elite technological circles, an industry where only a handful of nations have ever succeeded in building large passenger aircraft from scratch. For decades, airlines around the world had a simple choice: Boeing or Airbus, American engineering or European design, no third option. Even Chinese airlines, despite operating some of the busiest routes on Earth, had to rely on these Western manufacturers. The C919 changes that equation entirely. Its arrival challenges not just corporate market share, but also the geopolitical structure of global aviation. Predictably, this new competitor has triggered a response from those who've long controlled the industry. The United States, in particular, has viewed China's progress with growing unease. Washington's approach to rising technological rivals tends to follow a familiar pattern. When another nation shows potential to threaten American dominance in key sectors, containment measures often follow. According to recent reports from the New York Times, the United States Department of Commerce has moved to restrict export licenses that would allow American firms to supply critical technology and components to Chinese commercial aircraft programs. The target is clear: the C919. Some United States officials have been surprisingly candid about their aims. One analysis suggested that without continued access to American technology, China might struggle to deliver even 200 aircraft over the next decade, a projection assuming Chinese engineering progress will stagnate under sanctions. This leads to fundamental questions that extend far beyond aviation economics. Can the United States really slow China's aerospace ambitions through export controls? And just as crucially, how will China respond when faced with technological barriers meant to stall its progress? If you find this kind of analysis valuable, consider subscribing to stay updated as this story develops. Now let's explore the deeper context behind this high-stakes confrontation. When China officially launched commercial operations of the C919 in early 2023, skeptics doubted whether a homegrown aircraft could meet the rigorous demands of modern airline operations. Nearly 2 years later, the data provides a clear answer. The C919 has logged over 23,000 flight hours, completing more than 9,600 commercial flights, and safely carrying about 1.23 million passengers. For any new aircraft, let alone one from a manufacturer with no prior experience in this market, these operational stats prove real capability. Global reaction has evolved from curiosity to genuine interest. Airlines in Brunei, Indonesia, and Brazil are actively considering procurement options. In April, Malaysia Airlines publicly announced it was evaluating several Chinese-built aircraft, including the C919, the ARJ-21 regional jet, and the C929 wide-body airliner currently under development. Perhaps most noteworthy was a statement from Ryanair, Europe's largest low-cost carrier. In May, the Irish airline confirmed it was assessing the C919 and would consider placing orders if pricing came in 10 to 20% below comparable Airbus models. That announcement marked a turning point, the first time a major European carrier had seriously considered a Chinese commercial jet. For China's aviation industry, this served as validation from an unexpected source. Ryanair's business model depends on ruthless cost control and operational reliability. The fact that they're open to evaluating the C919 shows that Chinese aerospace engineering has achieved credibility that transcends politics. Yet beneath these encouraging signs lies a more complex reality. The path to full global market acceptance remains filled with regulatory and political hurdles that could decide whether the C919 becomes a true international competitor or remains a largely domestic success story. In aviation, airworthiness certification is the ultimate gatekeeper. Without it, no aircraft can legally operate in most major markets. Each certification isn't just permission to fly, it's an entry ticket to an entire aviation ecosystem worth hundreds of billions of dollars in related activity. For China, securing global certification for the C919 is among the most challenging steps toward international expansion. The potential economic impact is enormous. Each new market opened could generate supply chain orders exceeding 150 billion yuan. The certification process, led by American and European regulators, is deliberately exhaustive. It covers design philosophy, manufacturing practices, testing procedures, and ongoing maintenance requirements. Every component and system undergoes scrutiny to ensure safety under all conceivable conditions. While this rigor exists for valid safety reasons, it also creates formidable barriers for newcomers. Aircraft from outside the traditional aviation powers often face extended review timelines that can delay approval for years. The Boeing-Airbus duopoly that has dominated commercial aviation for decades makes this challenge even steeper. Together, they control roughly 98% of the global market for large passenger jets. Their influence extends far beyond sales. It's embedded in regulatory structures, supply chains, and airline planning worldwide. For Western regulators to grant full certification to the C919 would fundamentally alter this dynamic, validating a competitor that could redirect billions in revenue toward Chinese manufacturers. This context helps explain why certification progress has been slow, despite the C919's strong safety record within China. Regulators in the US and Europe face pressure not only to assess safety, but also to weigh the strategic implications of endorsing a Chinese rival. Now, the Trump administration has added another layer of complexity by restricting the technology that keeps the C919 in the air. To understand what's truly at stake, we need to look at what triggered this escalation. Starting in March of this year, the Trump administration launched so-called reciprocal tariffs targeting more than 180 countries and regions. China was hit especially hard, with tariff rates reaching an extraordinary 254% on certain goods, sending shockwaves through global supply chains and Chinese exporters. Beijing responded swiftly, imposing 125% tariffs on U.S. products, escalating the trade dispute toward a potential full-blown economic clash between the world's two largest economies. The aviation sector felt the impact immediately. American aircraft and components suddenly became far more expensive for Chinese buyers. Boeing, long reliant on China as one of its biggest markets, faced the possibility of suspended orders, potentially costing up to $28 billion in lost revenue. Eventually, both sides recognized the mutual damage and agreed to a temporary 90-day truce, reducing tariffs to 10% while talks continued. But stepping back from a broad trade war didn't mean Washington was easing up on efforts to restrain Chinese tech progress. In fact, the tariff fight paved the way for more targeted measures aimed at slowing China's growth in strategic sectors. By May, the U.S. unveiled its next move: export license restrictions on products and technology destined for COMAC, the state-owned manufacturer of the C919. These restrictions didn't target the aircraft's frame or avionics, but something far more vital: its engines. Here's where the C919's development strategy shows both foresight and vulnerability. While China has made major strides in aerospace design and manufacturing, one area remains notoriously hard to master: advanced turbofan engines. The C919 currently depends on the LEAP-1C, developed by CFM International, a joint venture between GE Aerospace from the United States and Safran Aircraft Engines in France. This isn't a minor component, it's the aircraft's technological heart. The LEAP 1C generates up to 135 kilonewtons of thrust and delivers about 15% better fuel efficiency compared to older engines. It's quieter, cleaner, and far more efficient, key factors for modern aviation economics and environmental standards. Unlike the LEAP 1A and 1B used by Airbus and Boeing, the LEAP 1C is supplied as a fully integrated propulsion system. It includes the engine core, nacelle, thrust reverser, mounting systems, and exhaust, all as a single package. While this integration improves maintenance efficiency, it also centralizes risk. If any key part of the system faces export restrictions, the entire propulsion package becomes unavailable. Roughly 30% of the LEAP 1C's components come from American suppliers. Even though Safran is an equal partner and manufactures parts in France, United States export laws still apply to any product with a significant amount of American technology. That means if Washington denies export licenses, even the French partner cannot legally continue supplying the engines to China. The consequences go beyond aircraft already flying. Potential customers in Vietnam, Kazakhstan, and other countries now face uncertainty over delivery schedules and long-term parts support. This interlocking web of technology, politics, and power is what makes the C919 story one of the most fascinating battles in modern aviation, a contest not only for market share, but for control over the future of global flight. For airlines making fleet decisions that will shape operations for decades, supply chain reliability is absolutely crucial. When engine availability becomes uncertain, even aircraft with attractive pricing lose their appeal. Hesitation spreads, orders get delayed, and momentum fades. From Washington's viewpoint, this serves as an effective pressure point. Instead of sanctioning an entire aircraft program, targeting the engine delivers maximum disruption with minimal diplomatic complication. But there's a key assumption behind this strategy, that China lacks the ability to build comparable engines domestically, and that this weakness will persist long enough for sanctions to have the desired effect. History suggests otherwise. When COMAC first launched the C919 program in 2011, Chinese engineers and policymakers knew they were stepping into territory dominated by Western technological expertise built over nearly a century. They also understood that relying on foreign suppliers for critical components could become a serious strategic risk. That realization led to a parallel initiative, the creation of the CJ1000A, an engine designed specifically for the C919 and developed entirely with Chinese technology. This wasn't just a backup plan. It was a long-term bet on China's ability to conquer one of aerospace engineering's most challenging frontiers. The Chinese government and state-owned enterprises invested more than $2 billion into advanced engine research and development. Their goal was ambitious, to produce a turbofan engine that could match or outperform the LEAP 1C in thrust, fuel efficiency, and environmental performance. Target specs called for over 13 tons of thrust, 5% lower fuel burn compared to Western models, and 40% lower emissions. Meeting these benchmarks required breakthroughs in material science, thermodynamics, precision manufacturing, and system integration. By 2023, after years of intensive development and testing, the CJ1000A reached a major milestone: high-altitude test flights mounted on a Y-20 military transport aircraft. The results validated years of work. Performance data showed the CJ1000A starting 12% faster than the LEAP 1C in extreme cold, a significant advantage for airlines flying in northern climates. It delivered 3% better fuel efficiency and 25% lower maintenance costs, thanks to a design that simplified servicing and improved reliability. In May 2025, the moment Chinese engineers had been working toward finally arrived. A A C919 test aircraft, designated B-02K, was fitted with CJ-1000A engines and began a comprehensive validation program. Over 500 flight hours, the domestically designed engines operated reliably across the full performance envelope. Today, the localization rate, the percentage of components sourced from Chinese suppliers, stands at 80%. A remarkable leap for China's aerospace supply chain. Technologies once thought permanently out of reach are now being produced at home. High-temperature alloy turbine blades, capable of withstanding heat that would melt ordinary steel, are now manufactured by Chinese metallurgy firms using proprietary alloy recipes. Ceramic matrix composite nozzles, which endure intense thermal stress while keeping weight low, come from domestic research institutes. Perhaps the most striking progress lies in turbine blade technology itself. Chinese scientists have developed special alloys that allow high-pressure turbine stages to function at over 1,600 degrees Celsius, temperatures where metal approaches its melting point. Creating materials that stay structurally sound under such conditions, while spinning thousands of times per minute, marks a true engineering triumph. The CJ-1000A's control system integrates thousands of sensors that constantly monitor operating parameters and stream data in gigabits per second. This real-time oversight keeps the engine running at peak efficiency regardless of altitude, temperature, or thrust setting, maximizing both lifespan and performance. Beyond hardware, China is also developing its own airworthiness certification framework under the Civil Aviation Administration of China, or CAAC. For decades, United States and European standards have been the global benchmark. By building credible alternative certification systems, China creates a pathway for its aircraft to enter international markets without depending on Western regulators, who might face political pressure to delay approvals. COMAC's production roadmap outlines the path from prototype to mass manufacturing. Initial CJ-1000A production is scheduled for 2026, with an annual output of 50 engines. By 2030, production is expected to reach 200 units per year, enough to support large-scale C919 deliveries independent of Western suppliers. This timeline matters immensely. The LEAP series engines have long dominated the narrow-body aircraft segment, powering both Boeing's 737 MAX and Airbus's A320neo families. The CJ-1000A now gives airlines a credible alternative, disrupting long-standing supply relationships and introducing competition where none previously existed. While the CJ-1000A fulfills China's immediate propulsion needs for the C919, the country's aerospace vision goes much further. The upcoming C929, a wide-body aircraft intended to compete with the Boeing 787 and Airbus A350 on long-haul routes, demands even more powerful engines. Enter the CJ-2000, a high-bypass turbofan engine with a designed thrust of 35 tons. This class of power is essential for wide-body aircraft that carry hundreds of passengers across oceans, often battling strong headwinds at high altitude. At this scale, the engineering challenges multiply dramatically. An engine producing 35 tons of thrust must handle massive air volumes, maintain high efficiency from takeoff to cruise at 40,000 feet, and run reliably for 12-hour-plus flights. The CJ-2000's design features a 12-to-1 bypass ratio, meaning 12 units of air bypass the combustion chamber for everyone that passes through the core. This configuration improves fuel efficiency and reduces noise, key priorities for both airlines and airport communities. The result is about 15% better fuel efficiency compared to the CJ-1000A. On a trans-Pacific route, that could mean saving 20 tons of fuel per flight and cutting operating costs by roughly 15%. Over thousands of flights, those savings translate into hundreds of millions of dollars. Technological advances in the CJ-2000 highlight just how far Chinese aerospace engineering has advanced. Directionally solidified single crystal turbine blades, which eliminate grain boundaries in the metal, have achieved rejection rates as low as 7.8% in production. This precision allows a 200 degrees Celsius increase in temperature tolerance, enabling stable operation at nearly 1,700 degrees Celsius. In March of this year, the core demonstrator, designated CJ2000C101, completed its first ignition test, later achieving 100.6% of its design speed, a crucial validation milestone proving the concept's soundness. Washington's decision to restrict engine technology exports to COMAC follows a clear strategic logic: identify a critical dependency, apply pressure there, and hinder a competitor's ability to grow. In theory, this should slow C919 production, discourage foreign orders, and help preserve Boeing's market position. But this reasoning depends on assumptions that no longer seem accurate. It assumes China's engine development will remain years behind Western designs, that quality will fall short of commercial standards, and that airlines will continue favoring established Western suppliers. Reality paints a different picture. Chinese aerospace engineers have compressed decades of Western progress into a few short years. While their engines may not yet surpass Western counterparts in every performance metric, they're approaching parity, and at a lower price point, that's often enough to sway airlines. Moreover, export controls are accelerating China's push for self-sufficiency while prompting international customers to seek more diversified, politically stable supply chains. Airlines that once preferred Western engines for their C919 fleets may now view Chinese alternatives as a form of supply chain insurance, less vulnerable to political interference. Timing also matters. Had these restrictions been imposed a decade earlier, when China's engine capabilities were far behind, they might have been decisive. Implemented now, just as the CJ1000A completes validation and nears production, they may be too late to achieve their intended goal. Instead, these sanctions could strengthen China's resolve to achieve complete technological independence. Cutting off access to Western components removes any remaining incentive for collaboration, reinforcing Beijing's conclusion that relying on imported tech exposes it to political risk. Each new restriction thus fuels support for domestic innovation, even if local solutions are initially more costly or less refined. Over time, this self-reliant approach could turn what Washington intended as a constraint into the very catalyst that accelerates China's aerospace rise.